When you're designing a system, especially for a new chip, it can be challenging these days because of all the different components involved. Could you tell us a little bit about the product that you have here that makes that job significantly easier?
Absolutely. So Mirabilis Design is in the business of providing modeling and simulation software for architecture exploration. One of the challenges that the system modeling industry faces is that everything has to be built custom. That is why you find a lot of companies unable to get into the system modeling space. What we have done different is built up the largest library of IP blocks. So which means if you want to put a NOC with, say, Arteris or CMN or your own proprietary one, we have building blocks for that. You want a processor, we've got building blocks. So within the single environment, all of these components are available for you that if you want to plug in, you can plug them all of them correctly. You provide your source code, you provide your workloads for your sensors, you provide camera interfaces, information, and boom, you can run a complete Monte Carlo simulation and start doing iterations on which architecture is better, why is it better. You get your power, performance, all of that statistics as well. So using that, you can speed up your architecture decisions.
So how do you define your structure? Is this something with a graphical system or you're just connecting the various pieces together?
Good question. So we're completely a graphical modeling environment. Our goal is for users to be focused on the architecture, not focus on programming. And so yeah, we allow you to do everything graphically. We provide you these what we call components of blocks, and each one of them is uniquely parameterized. So a UCIe block would be different from PCIe 6, would be different from AXI bus, and they would have unique set of parameters. So when you connect them all up together, you set unique parameters for each one of them, and then you can run off the simulations.
Okay. And what type of simulations can you then run? You can essentially test out the entire chip at this point?
It can be more than that. So test out. You can be testing out just the the processor subsystem, like the caches, the buses, and the memory, or the entire SoC. Or we have a lot of our customers that want to test it out in the context of an application. Like what happens if I put this in, say, the body control in a car, or what happens if I use this in, say, a rocket, or in, say, consumer electronics. So I have an RF thing for my Wi-Fi, and I want to see how it works in a consumer product. They can run a simulation of that and see what the net impact is. So am I being able to achieve the response time? Is my power below 5 watts? Is it, am I being able to, handle all the different activities that are requested off of me, either concurrently or sequentially? Being able to try out all those experiments.
Now, once I have this design, how do I wind up moving it into some of the other tool sets that finally get it into a fab?
Good question. So we're actually completely open in terms of our underlying infrastructure. So everything we do is JSON and XML based. So which means the user can actually get a complete view in an XML file. Now there's multiple ways it can be used. So for example, one of the things we can provide is on the verification side. So we can do VCD dumps, we can do traces that you can connect to a network. You can provide system Verilog code, your UPF files for power. So it generates all of those. From the specification of your actual development, one thing we do is the connectivity between all the individual components and the details for each of the components. So some of them could be IP blocks. So in those cases, the parameters are unique. Other ones could be actual logic. So we actually have a code that is underlying the thing that you can see. So the developer would actually see that code and write out his RTL or write out a schematic. So it provides you that. The other thing that it also provides you is it provides you your overall topology, which if you have your own in-house tools for generating netlists, this can be provided along with the parameter list, provided as an input, so that they can, they can actually, generate the automated netlist. So if you're a company that's got 80 to 100 chips a year, you don't want to go create each one manually. This becomes an automated process from your architecture down to your netlist.
So it also sounds like if I'm going to be doing different chip designs but having, commonality between them, this is going to allow me to both construct those and test each of the individual pieces.
Exactly. So we have a concept called templates. And so these templates become classes that you can instantiate. So for example, I have a processor template or an eFPGA template, or I have a, a chiplet scheduler. So I can set up all of those, plug them all together. So for my next chip, I find out, oh, I need more memory here. I don't have to do anything except for change the parameter. If I say I want to have 2 cores, we have something called dynamic instantiation. You can just change it to say run 2 cores, don't run 1 core. So you can very quickly put your next generation chip together.
Well, thank you very much for filling us in on
Sure.
how we can design systems.
Absolutely, appreciate the time.